Hello, everyone. We're very glad you could all join us today. I am Eli Leland, the CTO and co-founder at Voltaiq, and I'd like to welcome you to our webinar, where we'll be talking with our guest Celina Mikolajczak about ramping from pilot to Gigafactory at Lyten. First, a couple of housekeeping notes. So we welcome and encourage participation from our audience today. So please do submit your questions through the Q&A function of your Zoom app. And note that the participant chat is disabled for the webinar, so please do use that Q&A function to submit any questions you have, and we'll get to them toward the end. So our featured panelist, today is Celina Mikolajczak. Celina comes to us today with nearly 2 decades of leadership experience across the battery industry, including roles at Tesla, Uber Elevate, Panasonic, and Quantumscape. A good bit of manufacturing experience in there as well, as we'll talk about for the next hour. And on today's panel, Celina is joined by my co-founder and Voltaiq CEO, Tal Schulklapper. Tal has also been working on electrification technologies for over 20 years, with extensive hands-on experience developing and commercializing fuel cells and grid storage batteries before starting Voltaiq with me in 2012. So we will start with some material from our featured panelists, which will be followed by a discussion with the panelists. And then we'll save some time at the end for audience questions. And so with that, I'd like to introduce our featured panelists. Celina, please take it away.
Hey, everyone. Really appreciate the opportunity to chat with you guys, and thanks for inviting me. So I think Eli mentioned I've done a lot of stuff in batteries, and 2 decades, and I'm feeling old. So I'm officially old. It's okay. About a year and a half ago, I joined Lyten. It's a small startup in San Jose, and have been doing some interesting things there. Lyten is a very small startup. Came out of stealth, I think, maybe 2.5 years ago. So not something that a lot of people know about. Who are we? So we were founded back in 2015. And Lyten really is a company that's devoted to making 3D graphene materials. That's really the platform technology for the company. We apply those graphene materials to a lot of applications. So we do composite materials, we do sensors, we do some military work. And what I do is I lead the battery effort, and we are making lithium-sulfur batteries. About 260, 270 employees. A lot of researchers, and a small pilot line. Okay, so let me just start out with, what is 3D graphene? What does it look like, or how do we make it? What we do is we start with a light hydrocarbon like natural gas or maybe a biogas, and we put it through a reactor where it's cracked and turned into more complex carbon forms and hydrogen gas. Okay. Neat thing about this is, depending on how we run that reactor, we can make carbon in all kinds of shapes, and some shapes are better for certain applications and others for different ones. So we basically tune those reactors. If we're going to make carbon for composites, we make it one way. If we make carbon for lithium-sulfur batteries, we make it a different way. The company was originally founded to actually produce hydrogen for the hydrogen economy, which seemed like a great idea until the company founders realized that the black stuff that people wanted them to get rid of was actually worth more than the hydrogen. So the company pivoted and did carbon, and they were looking for, how do we apply this? There's all these interesting things. And some of the morphology that they were making, they looked at and said, huh, that's kind of interesting. They had some sponsors who were military guys, and, looked at those structures with the founders and said, if you could put sulfur in that, hold on to the sulfur, you could make a lithium-sulfur battery, and that'd be really game-changing. Why don't you try that? So the company started, and they started trying to make batteries with this, and has grown from there. The other nice thing about this process is that it is a decarbonizing process. So when people talk about, well, batteries, or how environmentally responsible is battery making, batteries are an industrial product. Yes, there's a lot of chemicals, there's a lot of energy used to produce batteries. But when you start with a decarbonizing process, there's an opportunity here to turn this into a carbon neutral battery chemistry, which would be like amazing because nothing else is close. Let's see. All right, so what is a lithium sulfur battery? Okay, when I first heard about Lyten and the boss started trying to recruit me, he said, "Oh, I got lithium sulfur." And I'm like, "What is lithium sulfur?" And I'm like, I'll open the battery handbook, and I open my version of the battery handbook. There's like a paragraph on lithium sulfur. And this book is like, I don't know, 2, 3 inches thick, right? So I look at this and I'm like, huh, this is obscure. Okay. Um, it's an obscure chemistry at this point, or it has been up till now, because what you're doing is you're using sulfur as the cathode and usually metallic lithium as the anode. And sulfur, of course, is insulating, so that doesn't really make for a really good cathode. Okay, you have to add something conductive to the sulfur. I mean, people will do this. They'll add various carbons to the sulfur and make it conductive and try to run this. But the other thing about a lithium sulfur battery is that it's not an intercalation chemistry. It's a conversion chemistry. And that's like, well, what does that mean? Well, it means that what's happening is inside the battery as it charges and discharges is really fundamentally different. In an intercalation chemistry, which is what lithium ion is, you take the lithium ions and you move them to the cathode, and they sort of squish into the cathode crystal structure, and they kind of make themselves a home in the open spaces, right? They don't react with the structure, but they intercalate into it, right? And then they come out, and then they go into the graphite, and they find spaces in the graphite to sit, right? So you've got these lithium ions kind of going back and forth, but not really reacting per se, or ideally not. With lithium sulfur, it's very different. You take the lithium from the anode, you move it to the sulfur side, and the lithium covalently bonds with the sulfur, right? So you have all kinds of chemical kinetics happening because you've got covalent bonds forming and breaking. And what happens is you take the sulfur, it's a solid, you start adding lithium to it, the lithium starts peeling off chains of sulfur, and those chains of sulfur become dissolved in the electrolyte. These are the polysulfides. So you're going from a solid phase to something that's basically a liquid. And then at the end of discharge, Li2S will precipitate out of the electrolyte and form a solid crystal again. So you're going from solid to liquid to solid. And you've got these polysulfides that in the liquid form are very mobile or potentially very mobile, which is why lithium sulfur has been such a challenging chemistry. What we did with our graphenes is we created a structure that will hold on to the polysulfides effectively, right? And help us control that shuttle and actually work with the sulfur. The graphene is also super conductive, so you don't need additional conductive additives. It forms that structure, that backbone, the caging, and so forth. So we can actually get it to work and work reasonably well. Okay. Not simple, but exciting. I should mention that, why go through all this trouble? I mean, lithium sulfur is, why do it? It seems painful. Well, sulfur is really, really cheap. Okay, you see sulfur in mountains, in port cities, where it's used for agricultural products. Okay, it is incredibly inexpensive compared to most cathode materials. It's even cheaper than LFP. Okay, so that's great. And then lithium sulfur has the potential to have energy densities that are 2 or, in the theoretical side, 3 times as high as what you get in lithium ion, right? So where, you might look at the top of the line of lithium ion cells being 300 watt hours per kilo, lithium sulfur has the potential to be 600. And then, people give you much higher numbers in theory, but I kind of like to be a realist and say, well, if we get to half of theoretical, we'll be good, right? So, a real roadmap to 600 watt hours per kilo is beyond what people can get in solid state, right? With an NMC cathode and a lithium metal anode. So there's a huge upside to that. So high energy density, low cost, super lightweight. Okay. Our 18650s, we make 18650s. They weigh half of what a conventional lithium ion cell in 18650 is. And, we can get lighter than that because the can is half the weight of the cell. right? People pick these things up and they're like, whoa. So this changes, the application. So if you've got a heavy vehicle, you want these cells in there because they're going to make that your curb weight problems much easier to deal with, right? So that's cool. And then the other thing is, how do you make these cells? Well, our systems basically work with conventional lithium-ion making tools, right? We have to do the 3D graphene fabrication. That's different, and we make our CAM, but that's fine. That's one process. Once we make a CAM, it goes into mixing, coating, electrode making, just like every other CAM, except that we can use water because it's a lower voltage system. So we don't have a whole NMP uh, uh, CapEx, requirement where we have to deal with NMP and, collect it, distill it, and all of that. So really straightforward electrode making. It drops into conventional electrode making tools. And then cell assembly is, again, pretty simple. We use modified lithium-ion tools. And by modified, I mean slight modifications. We got the tools in, we got them up and running on conventional lithium-ion cathode and anode. And then we spent, 2 months modifying them to work with our chemistry. So that's like well within the range of reason from a CapEx perspective and from a planning a tool system. And then formation is different. We don't have to form an SCI layer. We do have to charge and discharge the cell. There's some differences there, but again, the tooling is the same. So, this really drops into conventional cell making in the conventional cell making world. So when you look at, okay, can I make a factory? This stuff is like, yeah, okay, I'll buy conventional tools, make a few mods, and we're good, right? So we have a factory. It's a small pilot line. For those of you who've seen big manufacturing facilities, you're like, oh, it's adorable. I mean, we got one winder, we have one stacking tool. But it is about 2 megawatt hours capable, and it shows us, what we can do with the technology. And we're learning a lot about, the details of manufacturing the cell, and of course, making enough cells so that we can rigorously test and improve our technology. So, since we're talking about testing and data, just to give you a sense of, why we use Voltaiq software and how we use it, right? So when the boss first said, okay, this company should try lithium-sulfur cells, there were like, I don't know, 3 guys that they hired on to try making some cells. And they, of course, had to test some stuff. And so, they convinced the boss to let them buy one like used Maycore, I think, and it had some, small number of channels. I think it might have been 16. It might have been, like 48 or something. And then, they showed this thing this works. And so they started adding channels. So they started buying Arbons too, and biologics. So, early days, right, there were about 120 channels. Okay. And, that's like, nowadays you're like, well, that's kind of small. I mean, when I bought my first Maycore in the business 20 years ago, we had 16 channels and it was like a miracle, right? Um, so 100 channels, give or take, when a company's starting up, it's enough to test the stuff. So what did that mean? Well, you ran the cycles and you sat at the Arbon and the Arbon system, and maybe you used their software to visualize your data, or maybe you sent it out to Excel and then use Excel to, plot your data and visualize it. And, when you're starting out, okay, your engineers kind of spend some time and they pull data to visualize it. But okay, you've got one tester, maybe 2. You're trying to normalize between 2 testers. It's annoying, but it's kind of doable, right? So, okay, you'll spend, part of a day every day looking at your data. It's not terrible. It's not great, but it'll get you there, right? Okay, fine. That's 100 channels, right? What, but where are we today, right? Now we've got over 4,000 test channels, which is still pretty modest for cell development. Okay, but It's a good number of test channels. And, we got 2 locations, and we've got, 5 different systems that we're running for various reasons, because we are a startup and, we're going to buy testing channels from different vendors because they're available. So, if you're going to go at this with the Excel spreadsheets, it's just not going to work, right? Um, so, so we applied Voltaiq a few years ago. Um, and what it means is, our engineers now, they don't spend time on data management. Okay. They look at their data and then can do development. Um, and, you look at this and you're like, well, can you write your own? And when I was at Tesla, Tesla had its own system that they'd written, and they'd done it over a decade of work that they'd put in, putting together their own internal in-house system. And it required, about a dozen engineers to run it, keep it updated, and keep pulling reports from it, right? Same thing at Quantumscape. Quantumscape, founded fairly early. They'd had, a couple of decades of development on their internal in-house system. And again, it required a lot more admin. Okay, when I went to Uber and started doing Elevate, and we, bought some channels to start testing cells, I didn't have that kind of headcount. I didn't have that kind of time, right? Like, and that's when I first met Tal, and he showed us Voltaiq, and I'm like, oh, we need that, right? And then coming to Lyten, um, it was very clear that we needed Voltaiq as our system, because I really need my engineers to be doing engineering. It's a difficult enough problem we have to solve with lithium-sulfur, and how to manufacture it. And then, we've got all this data. We have to look at it. We've got different testers, and they're not even all the same age. We've got that early Makor still running around. The boss has been, like, I don't know, sentimental about it. Doesn't want us to get rid of it. I don't know. But, we've got old equipment, new equipment, and then, we're concerned about our data security. Someone gives an update, it's got to get you know pushed out to all the software. Things can't break, right? So, this is something where people think, well, it just sort of works. And it's like, well, your digital architecture is a tool in your factory, just like every other tool. And you'll do maintenance on big tools, right? And you have engineers running those big tools so that they work. It's the same with your digital architecture. It's not, it just doesn't just happen. It requires quite a bit of thought uh, and skill to do this well, right? So, so Voltaiq's part of our digital infrastructure, right? So we're like, okay, 4,000 channels, your lab, that's nice. What are you doing next, right? So just to give you a sense of our roadmap, we're at 2 MWh, right? That's nice. That makes about 200,000 small cells a year, which is respectable for a lot of things, but it doesn't get you to like EVs, right? So, if we're going to step up to this and say, okay, we're at 2 MWh, we want to get, first kind of a mini giga line running, a few hundred MWh, then we want to get into kind of a small gigafactory production over a couple of years, and then get to a gigafactory. You look at that and you say, okay, these things require all kinds of different scales of tooling, right? We've got a couple of small tools right now for a pilot line, and then you go in bigger tools for a mini giga, and then even bigger for a gigafactory. Your digital tools have to scale with that too, right? So that ability to scale a digital architecture that you've already spent a bunch of time building is really a bonus, right? So one of the things that I think it's important is that people figure out their digital architecture early, and then keep scaling with that, because it's really painful to change later, right? So anyway, so that's just a little bit about who we are and how we use Voltaiq. And you can look at the value proposition of lithium sulfur. It will be the next chemistry. It's going to electrify everything. It's challenging, but we're going to get there. Okay.
Wonderful.
All right.
Awesome. Well, thanks for that introduction, Celina. Yes, excellent. I can see our shining faces now.
Mm-hmm.
Cool. So just to back up a little bit, you touched on a couple of the roles and that you've had uh, in your talk, but can you just say like a little bit more about what your career progression has been in the battery space and yeah, what specifically interested you about taking on the role you currently have at Lyten?
Yeah, so as I mentioned, I'm old, right? So, when I was in school at university, I mean, uh, computers were just becoming a thing, right? Not everyone had their own. And God knows we didn't use laptops, right? We're all students sitting in a computer lab, like, in a little iMac screen. Um, Batteries were not a thing. Um, grad school batteries were not a thing. I went to grad school and I went to study combustion as a mechanical engineer, because I'd spent a little time in the oil field and I'd realized how hard we work to get petroleum out of the ground so that we can drive and run our society. So it seemed like combustion was kind of a relevant thing. People talked a lot about emissions at that time, and uh, uh, NOx emissions and soot and so forth. So that's what I went to study. Um, I got out of it, went to Exponent to be a consultant. I did a lot of fire kind of stuff. I did fire investigations. I did thermal safety stuff. Um, about a year after I got there, I got my first job in batteries, sort of. Um, I was asked to help put together a report on what the risk was of having people use cell phones at gasoline stations while pumping their gas. Like there was a period of time where everyone was freaking out that if you used your cell phone at the gas station, you would cause a fire, right? Like all of us now are like, what? But there was a time. So I did this report and put it together, and we went and presented it. And some guys from the Rechargeable Battery Association, PERBA, saw this thing, and they grabbed me and my colleague and said, we have a consulting job for you. Can you look at some stuff? Um, and so I got my first gig looking at the safety of batteries in air transport, which was, kind of a new thing. They were shipping button cells, little lithium metal button cells, and the first 18650s on aircraft, supporting the laptop industry. So I did a bunch of work on this. I did a bunch of ill-advised things. There was a sledgehammer, a parking lot, and a cell. Uh, I overwhelmed a fume hood, putting cells over Bunsen burners and watching them catch fire. I really don't recommend this at all. Okay. It's a way to really, really annoy your lab managers and the EH&S director, right? But, it was early days. So, at Exponent, we started doing, safety testing, and then people would start sending me burned up lithium ion cells in a Ziploc bag and saying, why to catch fire, right? It got into looking at cell build quality, uh, and doing a lot of work also for people to say, hey, if I'm going to pick between supplier A and supplier B, who's got the best quality, which one is going to be more reliable, which one is less likely to catch fire. So I kind of became an expert in why batteries go boom. And I was probably like, for a while there, the world's expert on why batteries go boom. Um, and then Tesla hired me to run cell quality at Tesla, right? Of course, Tesla was a startup. This was 2012. We were struggling to get cars out. And you know, batteries, they require a lot of stuff. I did a lot of things for Tesla and batteries, right? I started with cell quality. I did a regulatory work. I worked closely with the safety team. I started doing some of the materials work related to batteries. Yeah, I did a lot of things. After 6 years, I'm like, okay, time to go and do something bigger. So I went to Uber to lead a battery team. It was the first time I led a pack design team, right? That was a new and scary proposition. I'd never led a design team. Um, Hired a bunch of guys out of Tesla, right? They were experienced. They taught me a lot. Okay. Um, But Uber got out of the hardware business. So I went on to Panasonic to run engineering at the Gigafactory. Um, I had been with inside Tesla, I'd been, involved in manufacturing. I'd been the person who, every time the module line had trouble with their cells, it was me and my team going down there to troubleshoot this thing. So I kind of knew how to be in manufacturing. But running an engineering team for a factory is, again, a new experience. This factory is pumping out millions of cells a day. Uh, you don't stop, right? You fix the problems as they go along. Um, and the problems, you learn a lot about equipment. I mean, you think you know equipment, being a Tesla, I'm like, I kind of have a good idea of what's happening. I've been in a lot of these factories a lot of times. I've had quality issues we've had to investigate. We've troubleshot a lot of stuff. Yeah, and then you go work in a factory and you learn there's a whole lot more, like a whole lot more. Um, yeah, so, learned that. Came back to the Bay Area, went to Quantumscape, learned a lot about solid state batteries, learned a lot about trying to manufacture those. And then got recruited into Lyten. Um, the reason I looked at Lyten and it was this obscure chemistry, and I was like, the first time I got this phone call, I'm like, what? I'm like, is this a scam? Is this like really? Right? And I'm like, I started looking into it and then, and really looking into it and then talking with the CEO a bunch. Um, and, you know, I thought, well, Lighten's doing something very different. It's a very difficult chemistry in many respects, but it works. And one of the things that sold me is I went down to see them in the lab and they showed me 18650 cells, right? And that's like, it's kind of the old form factor, but I'm like, wow, you can wind this technology. Okay. If you can wind the cell, that means you can make it quickly on real manufacturing equipment. That moves the needle, right? So if you're going to make a lot of cells, if you're going to electrify everything, the manufacturing speeds are really important, right? Um, and I'm pretty convinced you can always make cylindrical wound cells faster than you can stack cells. Just like aerodynamics means that you'll push uh, way more kilowatt hours through a factory if you're winding than if you're stacking. So I look at this as like this is a cell that could really be mass market. I mean, the energy density is right, the cost is right, it's manufacturable. Um, if we can make this work, it has huge implications. And then there's the geopolitics that falls along with this, right? The supply chains right now um, are challenging. And then, you know, when I worked in the oil industry, it's an extractive industry. Um, I was out on rigs and I got to see what does it take to actually drill a well. And, you could say, well, that's not great, but it's actually pretty modest in its impact compared to a strip mine, right? And people are like strip mining entire mountains to do nickel extraction right now, right? So I look at this and I'm like, if we want to do electrification, if we want to do batteries, we have to do it in an environmentally appropriate way. Lithium-sulfur has that potential to really reduce the impact that making batteries has on the planet. So there were a lot of boxes that this company checked for me. So that's why I joined.
Wonderful. And you talked a bit about the production process and how it uses existing equipment. So I'm wondering, you said you took existing equipment and you spent a couple of months making modifications. So without giving away anything secret, can you give us some ideas of the kinds of things that you had to tweak, like and sort of taking your knowledge of standard lithium-ion production and adapting it?
Yeah, our electrolyte's a little different, right? It's going to react differently than a standard carbonate electrolyte. So you kind of go through the electrolyte filling machine and you kind of go, well, I need to change that piece, that piece, that piece, right? Because they're just not compatible, right? So you do some of that. We're handling lithium metal. So, that's sticky to certain types of rollers, right? So on and different pick and place equipment. So, you change a lot of materials, right, on this equipment.
Hmm.
And then the other modifications tend to be, stuff that's within the realm of doing a new design anyway, right? I mean, how you're stacking, how you're winding, what kind of tolerances you're going to hold. You're going to modify that routinely as you work through a cell design. So, it wasn't really, it wasn't really that different, that we didn't have to really change a whole lot, right?
Hmm.
Mhm.
Okay, excellent. And then just another little detail for those of us that are less familiar with some of the ins and outs of this stuff. You mentioned that your cathode doesn't require an NMP solvent.
Yeah.
Did I get that right? So
Yeah.
can you just say a little bit more about why that's an advantage for the technology, for the technology or for manufacturing it ultimately?
Yeah. So NMP is N-methylpyrrolidone. It is a solvent. It is an amazing solvent. Okay. I mean, you want to dissolve something, NMP is like amazing. It takes the paint off walls, right? Really. Um, it's used to dissolve a lot of binders for high voltage electrodes. So if you're going to be at 4 volts, you typically use PVDF as a binder. That doesn't dissolve in water. Okay. Um, and you run into various problems. So, uh, so to use these binders, you need a strong solvent. Now, N-methylpyrrolidone is also great because it vaporizes at a fairly low temperature, but not too low, right? So it mixes really well. It goes into the coater really well. In the coating process, in the heat, you'll drive off the NMP very effectively. And then what you have to do is you have to recover the NMP, right? Because you're not going to dump all these solvents into the atmosphere and they're expensive, right? So, so what happens is you you get the effluent from your coater, and then you have to condense the NMP. So you put it through like a big water spray system to knock the NMP, to cool everything out, knock the NMP into a liquid form. So then you get this like mix of water plus NMP that now you have to redistill, right? So you send this off to a big distillation tower, and um, you distill the NMP and you separate it from the water, right? And then you have to make sure it's super pure again, and then you'll dump it back into your process, right? So in many ways, NMP is great because it allows you to do that. And if you run the system properly, once you've got the NMP in there, it works pretty closed loop. You'll only add a little bit of NMP periodically, and you'll pull some sludge off the bottom of your distillation system for disposal. Um, Great. Except you've got this huge capex like cost for, this giant distillation system, all this recovery equipment, and running, and you OpEx to run it, right? And then NMP is, like any strong solvent, it's got implications for, health and safety, right? NMP was traditionally used for parts washing. So, it's not like it's not the worst thing you're going to encounter, but at the same time, exposure matters, right? And you don't want to expose your workers, right? So
Hmm.
EPA and the European Union, they're really trying to reduce the use of NMP, right? So there's more stringent regulation required now for handling NMP, and the Europeans are trying to phase it out. So, this has huge implications on conventional lithium-ion battery making because you don't make high nickel cathodes. First of all, you need the binders that are only dissolving in NMP, and second of all, you don't mix those with water anyway because you'll destroy the cathode powders, right? So
Hmm.
for conventional lithium-ion, it's pretty much NMP, or you go to the dry cathode approach, right? That people are doing where they're like,
Right.
trying to not use a slurry at all. That's really challenging. The dry cathode approach, people have trouble with it. It's harder than it looks. Um, Being able to use water as the solvent is just really convenient. You can use traditional wet coating. You don't have to have all that NMP capex. You don't have all that issue with the um, hazardous material, and it works really good, right? So that's why.
Awesome.
Mhm.
So shifting gears to some of the actual like hands-on work that your team has been doing, what have been the key challenges just in bringing up that 2 MWh pilot line? And I would sort of extend it to like, what do you anticipate going from there to the, you had that nice progression of scale. So like, what have been the challenges getting to this point, and what are the next stage of technical challenges that you and your team anticipate?
Oh, it is. Manufacturing cells is always harder than anyone thinks, right? And the faster you make cells, the harder it is to tell what's going wrong, right? So, when you're making cells by hand in a glove box or, on a bench in a dry room or something, you can kind of see what's happening really well, and you kind of know, okay, you know, are my like die punches getting kind of dull? Because you can see it, sort of, right? And and you make the cell and then it doesn't work, and you're like, something didn't work, and you open it up and you look, whatever, and you're at slow speed so you can see this thing. You go to a pilot line and you press go, right? On a like a punch or something that's punching, die punching, or on a winding machine or whatever. And it starts moving and there's a lot of stuff happening, and you can't see it all anymore. Like if it's a slow line, you can mostly see it, right? So you want to start with a slow line because because you're going to find a lot of problems, right? You're going to say, oh, I'm having something wobble and I'm not getting the right alignments. Okay, well, what do my alignment really need to be? Well, maybe it's this, maybe it's that. You go and you try a new, you might try a new aluminum foil, right? And it just has a different stiffness, and so now suddenly you have to adjust in either your stacker or your winder or punch die because it doesn't work like the previous one. And that's a lot easier to do first on a slow line to say, okay, I think I know how to dial this in to actually produce. But then you'll produce a bunch of cells, right? So, you know, a good, a good modest day, one shift, the pilot line can produce 100 cells. Now you get those all on test. And someone's got to put them on test and look at the data, right? And this is what people also sometimes underestimate. You really have to live in a sea of data with cells. Like with other products, you can run a test and you can be, does it work? Does it not work? Right? Um, but with cells, because of the fact that you can't see what's happening inside the cell, the tolerances that you're aiming for are often in the microns. And you make a lot of them. You have to look at a lot of data, right, to know if there's good or not good. Um, you can't avoid it, right? So, people are like, they'll make this mistake. They're like, okay, we make cars, therefore we should be able to manufacture cells. It's like cars are big and they're complicated, and but making cars is hard. I know because I was a Tesla and we struggled with that, right? But a lot of the problems with car making, or one of the key problems there, is like just the logistics of getting all the parts that you need to make a car at the line at the same time or when you need them, right? That's like huge issue with cars. With cells, the parts are not usually the problem. They can be a problem, but they're not usually the problem. The problem is your takt times are really short and your tolerances are really small and you can't see what's happening, and you're making a lot of cells, right? And you're burning a lot of material making a lot of cells. So, what's good, what's bad? Like, people made cars before they had computer systems and before they could, really track all this data. And they made it by hand and they had various quality checks, and you can do it, right? These days, people have an MES system on their automotive line, collects a lot of data. It's helpful, but in the end, you put the car on a dyno or you drive it and you know if it's good or bad, right? With cells, you don't make lithium-ion cells unless you can manage a lot of data. And I think that's part of the reason, like, why lithium-ion cells became a thing when they did, because you could start to really look at the data, right? And then high-speed manufacturing relies on even more data, because you get a tool that's out of whack, you have to know really fast, or you make thousands, tens of thousands, millions of cells of scrap. And, if you've ever had to scrap out 1 million cells, it is painful, right? So you live in a sea of data, and that's where that digital infrastructure is so important. And a lot of people overlook it because it's just not like it's not central to a lot of things that people manufacture, right? It is central to cell making.
Yeah, it's a new way of thinking in a lot of ways. It's,
Yeah.
everyone's got the old school, mechanical engineer and chemical engineers, we can model the system, build it out. And I think one of the things just, listening to the talk, just one thing you commented on is like 4,500 channels, that's seems like a lot to some people, but the reality, as you said, is like that's actually rather small for a larger cell development program. And I think just a couple of things. So just like the amount of, let's dig into this like amount of data. So we talk about development programs, you need a lot of data. You talk about all these process optimizations and tolerances you're trying to figure out. It's like, it's not just that end of line, it's the materials data, it's the process data, and just even at scale, just one of my favorite quotes from you is still the, high volume, gigafactory scale production. It's an unstable equilibrium. There's always something trying to push you off. And just be interested just to dive in a little bit about that.
Yeah, so you're the type of data you consume is a little different in like an R&D phase, right? You're really looking at that cell performance data and you're trying to dial in the performance, right? And then, with a pilot line, you're trying to do that, but then you're also like, how come some of my cells are sucking versus the other ones, right? Like what, where did I get something wrong so that, I've got this big distribution in my manufacturing data, right? And you're trying to dial that in, so you're trying to understand, how sensitive is my cell performance to, my loading, right? So how tight do I have to keep my loading tolerances, or how tight do I have to keep my electrolyte fill tolerances, right? So you're trying to figure that out, okay? When you get into mass production, you figured that out in theory, right? And so you want to make sure you're in that range, right? So you're setting a lot of, trying to make sure your stuff's still in spec, right? But then other stuff will creep in on a manufacturing line. People assume, oh, I'm going to set my manufacturing, I've got my quality metrics, and then I'm just going to run. And the thing about cell making is that as we talked about, it's an unstable equilibrium. Things are changing, right? Your suppliers for the various materials, they're just going to be a little different every time, right? And maybe something will creep in there that you didn't expect. Material's still within spec, right? Your quality guys put the stamp on it. Yep, we did IQC, it meets, but it's just a little different. And it means that, maybe your cell doesn't uptake electrolyte the same way. Maybe it takes a little more, maybe it takes a little less. Does it matter, right? What's your, are you scrapping out cells suddenly, right? So you're kind of monitoring the process. You're looking for trends. You're looking for drift through a lot of data. And what you're doing is a lot of times you're correlating, you've got a drift in manufacturing. You're like, is it okay? You look at your post-formation data and you say, am I seeing a drift in capacity? Am I seeing a drift in rejects? And then what you're also doing is you'll pull some cells from, every lot or every other lot or some, once a day or whatever, and you'll have them on cycle testing as well, right? So you're kind of looking at long term as you cycle cells out, what, if stuff was drifting, what was the implication on long-term performance of my cell? And then you're trying to correct this and dial this in because, you want to reduce your scrap rate because your margins, bad scrap rate, you're not profitable anymore. The margins are not that big. So you're trying to always reduce scrap. You're also trying to, reduce your warranty impact, right? So you're sending cells to customers and, if a lot of them come back with, yeah, this didn't meet our lifetime expectations, you're gonna pay a lot, right? So, so you're trying to consistently improve that. And of course, as you do this continuous improvement in your factory, right, you can say, okay, well, I can offer a more stringent warranty to my customers, right? I can offer a better price to my customers if I bring my scrap rates down, if I can increase my production speeds. Doing all of that really requires a huge amount of study of the data that you collect, right? So that's how sometimes you can see that, oh, a machine is breaking or I'm getting lots of alarms or I'm getting lots of rejects. What's the problem? And I, can go in there and try and fix it with a continuous improvement project. But other times you're like, I don't know, I'm just getting scrap on this line. like, you know, this line particularly runs high on an OCV rejects, right? I get more contaminants in this line. Well, where did the contaminants come from? Did they show up in your electrode making? Did they show up in your winding machines on that line? Did they show up in, you know, can insertion? Did they come from the cans? Did they come from when you crimped the cans? You know, welded the cans? What did they come in through filling somehow? Like, where is it? And there's like hundreds of steps down the line, and you're trying to, you know, shift, you know, you're not going to have a lot of these failures. You're going to have, you know, a ppm, right? Or like a fraction of a percent failure. And so you're like, well, I can't see it. I go stand by this thing. I'm not going to see it. You have to use the data you've collected about, you know, correlating which cells, which process, you know, what's the impact on in my data, and then you can narrow down to the tool if you're lucky, right? And you can start making adjustments there, and you know, or the process, or it's, you know, I've got one lot of material that seems to be bad, or one supplier that's having trouble, right? You narrow that down, you keep working that, and that's how you actually, you know, make one of these factories work, and that's how you actually go from, like, you know, wrapping $100 bills around your cells to, you know, being profitable.
Yeah, it's interesting. Just looking at some of the audience questions here, we're starting to get some questions about ML and AI, and I think you mentioned this, like just the infrastructure that you need to be able to do that. There's a lot of that in the press, in academia. You go to a lot of these companies, they're still reporting data in Excel. It's not even uniform. You look at companies who've done larger, you know, IT infrastructure projects, and like the data's in 3 different data lakes internally. Like, it really is important to build that underlying infrastructure and put the data in one place so people can start looking at those correlations, can start tracking these drifts.
Yeah.
If you don't have that together, it is a large project. It is, you know, equipment with PLCs from all over the globe. It is a challenge, but that effort is worthwhile. It really does speed things up.
Yeah. Yeah, it does, but it is not an easy project either. I mean, you spend, you know, that's where people are like, oh, we'll have like a couple of data guys, right? It's like, no. You're gonna need, you know, a serious data team, even if you've got all the best tools, and if you've done your due diligence on the digital architecture, you're still gonna need a lot of data guys, right? But at least you have a shot at it, right? So yeah.
Yeah, I'd love to dig in a little bit more on that. So you talked through this kind of root cause loop, right? Whether you're at the unstable equilibrium and things are pushing you off of it, and you're trying to figure out, you know, whether you should care about that or what the impact is, or something's going wrong, you don't know.
Yeah.
Can you talk a little bit more about, in that kind of root cause loop, how the digital architecture plays into that, and what are the different components that enable you to perform that?
Yeah. Yeah, so a lot of times you're pulling whatever you got, right? So, you know, you may have data out of I mean, the most typical thing is you'll see your post-formation data. You scrapped a lot of cells in formation, right? And conventional lithium ion, it'll be you know, probably some form of a contamination, right? A little defect, right? There, or you might have something where, yeah, you're just getting burrs and stuff shorting, or something's happening like that. That's the typical failure that you're going to then start looking for, right? So, you know, first of all, you have to see it in formation, right? You have to actually track and say, okay, I've got, you know, high scrap rate of cells. And then you're asking, well, which cells, right? So are they all coming from one particular line? Are they coming from your assembly line, one line, or is it coming out of electrode? Like, does this data correlate with all the cells that are coming from one batch of electrode, or one electrode line, or one assembly line, or one supplier of a raw material, right? So you can be going back into data, and you're kind of hoping that first of all the problem's in formation, and someone forgot to like change the pins in the formation testers, and you've got like a bad pin issue, right? You know, it's like, is it all coming from one tester, right? That's like the first step. Yeah, you get out of that, and then you're like, okay, is it all coming from one line? And a lot of times assembly is where you'll have like a lot of opportunities for contaminants to come in. So you're kind of like, betting it's assembly, right? So then you start looking at, where are these cells coming from and do they correlate to one line in particular? Sometimes you're lucky and they do. Sometimes they don't. Sometimes it's like, if it's a incoming materials issue, you'll see it across all the lines, right? Usually also like one coating line is feeding multiple cell assembly lines, right? Um, so, you're doing tons of data correlation. You need to know the history of where your cells came from and the materials that went into the lines that were there, right? So, you know, defects, like I said, they can be coming from any number of places. So one of the big things you're doing is correlation, right? And then after that, you're saying, okay, I've maybe knocked it down to uh, a particular process in assembly that's causing the failures. Is it the process that's causing the failures, or have I got one of the material inputs to that process and that process, something's interacting there where I'm getting lots of failure. So then you're like, you're looking at this as a time series thing. Is it always happening? Is it happening all the time? Or is it happening, only after certain things occur? Is this a maintenance issue? If they clean the machines, does the failure rate go down? And then it kind of creeps up again, right? So, you're correlating like everything you can think of, right? Sometimes you'll say, well, is it a certain shift of operators, right? But sometimes it's also like, other things that happen in the factory at certain times will impact what's happening on the line. So it's not that team of operators. It's the fact that there's some other process that kicks on in the factory, right? That could be impacting uh, your cell like quality, right? So you really, you really have to take this very broad look. And, it's one of those things where uh, you can do it, you can start with data correlation, but it goes a lot faster if the person looking at the data understands what actually is happening in the factories, like where the likely spots of problem are, or what's the implication of, my stuff coming out of this particular process or something, and what else should I look at? So you really have to have your analysts, your engineering team, um, really talking to each other and, working closely together because, um, some of the stuff, it's kind of subtle, right? And you think, oh, I should just be able to root cause this to, oh, I have a wearing tool, and sometimes you can, but
Like peeling
sometimes,
back the onion for some of these
yeah,
things. And
yeah.
the coating thickness, is that from, could be from the humidity. You don't have that instrument, like until you have
Yeah.
everything instrumented.
Yeah, well, even then, it's like you think you have everything instrumented, you don't have everything instrumented, right?
Yeah.
There's just no way, right? So, and if you, then people will complain, well, you're over instrumenting everything. It's like, well, and so you have to do that balance, right? Of like, am I getting useful data, or am I just creating, sensor reliability issues across my factory, right? So, yeah. Mhm. Yeah.
Interesting. So we have another. There's a question from the audience. You mentioned 18650 cells at Lyten. So are there plans to go to larger formats? And in general, what are the challenges in scaling up in format?
Yeah, so for our chemistry, actually, 18650 is not the best cell format because, like I said, the can is half the weight of the cell. Um, but we have some customers that are very committed to 18650, so we needed to make some for them. But our next step is we're gonna start converting lines to make 2170s, converting the line to make 2170s this spring, because we have some other customers that are deeply committed to 2170. Um, the question becomes 4680, right? And then, we also make pouch cells, right? So we make like 10x7 pouch cells. They're kind of small like this. And people are like, can you make it big? Right? And we're like, well, sort of, yeah. Um, the thing, the thing about big cells, so um, our chemistry, right? Like 4680 is probably a really good form factor for our chemistry just because of the way, the weights of the components versus the electrodes work out. Um, we'll try it eventually. But when you're making cells, and you're starting out, there are so many things that you have to get right, and it's so easy to mess it up. And a lot of times too, you're still in development. Your materials are not super cheap. I mean, they're, in theory, they're super cheap, right? But you're trying some new things, right? And you may not have, a big supplier keyed up where you're getting volume discounts or, volume pricing. You're buying stuff, from Sigma-Aldrich, right? And it's expensive, right? So it's this is why, by the way, people start their development in coin cells because it's very small, it's very cheap, right? You move up the scale from there. But um, like electrode making is there's a lot to it. And to try, if you don't make the a really good electrode, nothing else in your cell is going to work well, right? So, you look at, well, how uniform can I make my electrode? And, an 18650 electrode, maybe a meter long and, you know, 60 millimeters wide. Um, can you get that right? Can you make it uniform? Can you make it without defects? Can you manage it and assemble it without defects, right? You start going bigger, you have to get better and better at making your electrodes, handling your electrodes, managing them so that you don't add defects. Okay. So, people say, well, just make a big one. And it's like, well, you're going to have a lot easier time ramping up if you start with small, just starting there. And then, you've got you're going to have quality problems, right? You're going to have cells that are not going to work. It's really painful to scrap out a 100 amp hour cell, right? Really painful. It's not so painful to scrap out, a 2 amp hour cell or 3 amp hour cell, right? So, you go to your management and you say, yeah, we had a problem and I scrapped, X number of cells, right? It's a whole different discussion when they're huge. And, when you're starting out, you cannot expect that you're going to turn on these machines and they're going to just run. You're going to have trouble going there. So, do I want to go to big cells? Somewhat. I don't want to go to really big cells. I don't think it's economical. I think even a good manufacturer uh, has to do a calculation of, what's my scrap rate going to be? What's the cost on that? And, I don't think it's necessarily economical. I also, think really big cells pose some reliability issues in the final end product that, make it less cost effective than people think. But
Indeed, yeah. For folks in the audience interested in learning more, there's lots of stuff online, including we have some blog posts on some of the stuff about the fallacy of larger batteries or how they're actually very difficult to make because of defect density driving quality and things like that. And also we have a lot on there about how scrap rates drive economics of manufacturing and such. So I wanted to take one last question from the audience before some closing remarks, and we just have a couple short minutes left. But somebody asked, what's your advice for researchers and PhD students who want to learn more about battery manufacturing? Because it can seem like understanding how batteries work and why, and understanding how to actually make them at scale are two completely different things. So for those that are really deeply immersed in the academics, what's your advice for folks that are interested in getting more into the manufacturing side?
yeah, that's a really good question because you're right. The person asking the question is right. I mean, you're working in a lab and you're like, can someone make this? Can they use it? How useful is it? It's really powerful to get that manufacturing experience, like really powerful. Um, you know, I've been lucky enough to get it in cell manufacturing, but you can learn a lot in any manufacturing, job that you might take, right? You get in and you start seeing how people think about manufacturing and, you know, what's happening in the factory? How do people track things? How do they move things? So it's really useful to take a manufacturing gig of some sort just to start to wrap your head around it. If you can get some time in cell manufacturing, it's really worth it. I can say, can you take a tour somewhere? It's really tough to get in to tour these factories. They're very proprietary. But yeah, trying to get in to see some of this stuff and then trying to make some of this stuff yourself is like really powerful. So, and it does impact the way you think about research and and what you push a research team to do, right? So, my guys will come to me and they're like, "Hey, we got this great additive or something," and I'm like, how much is it going to cost and how toxic is it, right?" Because I'm like, eventually you got to buy this thing and then you got to like manage it in your factory, and you're like, "Yeah, no, you're not going to do that. That's like, just not something that you're going to be able to manage in the factory effectively, right?" So it does tend to, drive you in certain ways.
Yeah, indeed. And maybe Tal, you can speak to. So, we're fortunate at Voltaiq to actually have some folks on our team, across our team, including software engineering and who have actually experience working at the Gigafactory and other battery factories. I wonder, Tal, if you can talk about how that was important to bring into the DNA of our company.
Yeah, I think it's super critical. And I just think it just, as Celina said, is one of the key pieces of advice I give to people in school. Just go get your hands dirty, find an internship, go find a professor to work, whatever level it is, just, it's the academic knowledge that you have. It's really, it's at the end of the day, most of the time in your career, it's not going to directly apply. It's just that ability to learn, figure out stuff, see new things. But yeah, it's really, I think that's one of the key things that's really differentiated Voltaiq at the end of the day, is just really having tools built by battery engineers for battery engineers, and just having that understanding of what's going on, that domain expertise here has really been key to us, especially now as the industry is trying to ramp up. You need to get from point A to point B very quickly, whether it's producing cells, hitting that product milestone or whatever it is. And you just need tools that are really built around doing that, and then a team that really understands that, what their customers are trying to do with it. Because it's not just an Excel, everyone plots what they want. It's really about how do you get to that point A to point B, and you really need tools that are built around that at the core. And so you need people who've done that, and we've got those from our battery engineers working in customer success with our customers to our quality management team on the software side. These were quality managers at Penna and others. So it's that really has been a key differentiator for us, and one of the things our customers constantly call out.
Awesome. All right. Well, thanks again to our featured panelists, Celina Mikolajczak and my co-founder Tal, for joining me in this last hour. And thanks to all the audience. And please stay tuned for our next installment of our webinar series. And thanks very much, everybody.